Here we have the function f of x equal to the square root of 5x. And we want to find the area of the region bounded by the graph in the x-axis from 0 to 2. So we want this region right here. And we will use what's called Riemann sum. So we will find a Riemann sum for this region right here. And to use Riemann sum to find a Riemann sum, we will define we will form a partition of the interval from 0 to 2 as follows. Let x of 0 be 0, and then let x of 1 be 2 times 1 squared divided by n squared. And so in this case, if there are 4 rectangles, if we fill this region with 4 rectangles, then n would be 4. And then x of 2 would be 2 times 2 squared divided by n squared. And so in x of 3 would be 2 times 3 squared divided by n squared. And then all the way up to x of n, which must equal to 2, since the bounded region is from 0 to 2. And so here's an example. Suppose we fill this up with 8 rectangles. And so here we fill the bounded region with 8 rectangles. And notice the rectangles, this time the widths are different. And so this is rectangle number 1, number 2, number 3, number 4, number 5, and so on. And so x of 0 would be 0. And this time there are 8 rectangles, or there are 8 subintervals. And therefore n is 8. And n squared would be 64. And so x of 1, so this value right here, would be 2 over 64. And then x of 2 would be 8 over 64. And then x of 3 is 18 over 64. And then this right here, x of 4 would be 0.5. And then x of 5 is 50 over 64. And then x of 6 is 72 over 74. And then x of 7 would be 98 over 64. And then the last one, which is x of 8, which must be 2. And therefore, next we'll calculate the width of each rectangle, and notice that the widths, they are different. The width of the first rectangle will be x of 1, which is this one, minus x of 0. So it would be x of 0 is 0, and so it would be just 2 over 64. And then the second rectangle, the width will be x of 2 minus x of 1, and it will be 6 over 64. And then the third rectangle, the width will be x of 3 minus x of 2. And that comes out to be 10 over 64. And then the next width will be, the width of the fourth rectangle will be 14 over 64. And so on. And then we can go on and find the width of the fifth, the sixth, the seventh, the eighth rectangle, in which we will. But in general, if there are n number of rectangles, then for this particular example, the first width will be 2 over n squared. The next width, the width of the second rectangle, will be 6 over n squared. And then the third rectangle is 10 over n squared. The fourth is 14 over n squared. And so let's get a formula for the ith width. X sub I, as we saw up here, since the x of 0, x of 1, 2, 3, all the way to x of n is defined like this, and therefore in general x sub I will be 2 times I squared over n squared, if we're using this pattern. So this is one way of defining x of 0, x of 1. There are many, many ways to define x of 0, x of 1, x of 2, and so on. But we chose to use this pattern. So whatever pattern we choose, the first must be 0, the last must be 2, since we're going from 0 to 2. But x of I is, in general, is 2 times I squared divided by n squared. And so the width of the ith rectangle will be x of I minus x of I minus 1. So this is x of I and this is x of I minus 1. And so we have 2I squared over n squared, and then minus x of I minus 1 is 2 times I minus 1 squared, dividing by n squared. And so here we get 2I squared, and then I minus 1 squared is I squared minus 2I plus 1. And then multiply this out, we get 2I squared minus 2 times I squared is minus 2I squared. And then minus 2 times minus 2I is plus 4I. And then minus 2 times 1 is minus 2. And then 2I squared minus 2I squared, 0. So what's left is 4I minus 2. And so this will be the ith width. And so, for example, if we pick the, we want to know what is the width of the 8th rectangle, then it'd be 4 times 8 minus 2 dividing by 64. If we want to know what is the width of the 5th rectangle, then it'd be 4 times 5 minus 2 dividing by 64. And so in this example, we saw that there are 8 rectangles right here. And the one with the largest width is the last one. And the width of the largest subinterval is called the norm. And so this width right here, this is called the norm of this partition. So the largest width is called the norm, and is denoted as the double bars here with the delta inside. So this represents the norm of a partition. And the norm of the partition is the largest width of the partition. And so for this particular example, the norm will be 2 minus, right here, this is 1.53125, which is equal to 0.46875. And then notice that if we allow the norm or the largest width to approach 0, then there will be an infinite number of rectangles. And so this is the norm right here, and if we allowed it to approach, to get smaller and smaller and smaller and smaller, then the only way that can be done is if we fill this with an infinite number of rectangles. And so meaning as the norm approaches 0, then n, the number of rectangles or the number of subintervals, must approach infinity. And then the converse of this is not always true, meaning we cannot say as n approaches infinity, then the norm will approach 0. In general, it's not true, because there are examples where n approaches infinity, but the norm does not approach 0. And for this particular example, and here are the widths of the rectangles. So the first width is 0.03125, and the second width is 0.25. And so this point right here, this is 0, and then the x of 0 is 0, x of 1 is 0.03125, and to find the height of the first rectangle, we will use the right endpoint method. And so if x is 0.3125, then the y will be 0.395. And so that would be the height of the first rectangle. For the second rectangle, this x of 1 is 0.3125, and then this right here is 0.125. And we will use the 0.125 to find the height of the second rectangle. And so when x is 0.125, the y is 0.79, and therefore the height of the second rectangle is 0.79. For the third rectangle, this right here, it'd be x sub 2 to x sub 3. And this is 0.125, and this is 0.028125. And we will use the right endpoint, which is 0.28125, to find the height of the third rectangle. And so when x is 0.28125, the height would be 1.18. So the height of this third rectangle right here is would be 1.18585, which is this number, and so on. And the heights of all 8 rectangles are found right here. And then the areas would be just the width of each rectangle and times the height. And so here's the area of the first rectangle, the second rectangle, the third, and then all the way up to the 8th rectangle. And then what we do is we add these areas up, add them together, and when we add them together, we will get a number of 4.595184. And so the shaded region has an area of approximately 4.59. But notice that the rectangles that we use, they are larger than the shaded region, and therefore this value right here is much higher than the actual value, higher than the area of the shaded region. And so next, what we like to do is fill this up with an infinite number of rectangles where the widths are different. And when we do that, we will get the exact area of this shaded region. And once more, we have chosen to do a partition of the interval 0 to 2. We chose this type of partition. And therefore, x sub I is 2 times I squared dividing by n squared, where n is the number of subintervals or the number of rectangles. And then earlier, as explained, we found that the ith width, or the width of each rectangle, is 4i minus 2 dividing by n squared. And this is the function we're dealing with, and the x sub I is 2 times I squared dividing by n squared. N is the number of rectangles, and then the ith width, the width of the ith rectangle, is 4i minus 2 dividing by n squared. And therefore the height of the rectangle, we using the right endpoint method, will be the square root of 5 times x sub I, but x sub I is 2i squared dividing by n squared. And so we get 10 over n squared times I squared. And it will be the square root of 10, the square root of n squared is just n, the square root of I squared is I. And so this is the height of the ith rectangle. Now let's get the area of the ith rectangle. And so the area would be the height times the width of the rectangle. But the width is this. This is the width of the ith rectangle. And so it would be the height of the ith rectangle times the width of the ith rectangle. And so we get the square root of 10, and then n times n squared is n to the third. I times 4i is 4i squared, and then I times 2 is 2i. And then let's go ahead and multiply this out. Then we get 4 times the square root of 10 dividing by n to the third times I squared. And then minus 2 times the square root of 10 dividing by n to the third times I. And so this is the area of the ith rectangle. And now we want areas of n rectangles. So let's find the sum of areas of n rectangles. And so it would be summation from 1 to n. So this is the sum of areas of n rectangles. So in the example we have just done, n was 8. And so we would go from 1 to 8, and that will give us the sum of the areas of 8 rectangles. But this is summation of a difference, and so we can write it as the difference of summations. So a summation of a difference is just summation of just difference of summation. And then this is constant because the summation is with respect to I. So this part is constant, so we can place it in front of the summation sign. And same thing here, this 2 times the square root of 10 divided by n to the third, we can place it in front of the summation sign. And now we need a formula for the summation of I squared and the summation of I. Summation of I is n squared over 2 plus n over 2. And summation of I squared, where I goes from 1 to n, is n to the third divided by 3 plus n to the second divided by 2 plus n over 6. And so in the place of summation of I squared, we will replace it with this. And then summation of I will replace it with this. And that's what we have right here. And now let's multiply this out. This 4 over the square root of 4 times the square root of 10 over n to the third times n to the third over 3. That would give us 4 times the square root of 10 over 3. And then this term times n squared over 2, that would be 4 times the square root of 10 over 2n. And then this term times n over 6 is 4 times the square root of 10 over 6n squared. And then next we have 2 times the square root of 10 dividing by n to the third times n squared over 2. And we have a minus right here, so that would be minus 2 times the square root of 10 dividing by 2n. And then this times n over 2, it would be 2 times the square root of 10 over 2n squared. So this is the sum of areas of n rectangles. And we want the exact area, then we need to allow n to run to infinity or allow the norm to run to 0. Once again, the rectangles, they all have different widths. They have different widths, and the largest width is denoted as this symbol right here. Is called the norm. And so if the norm runs to 0, then the number of rectangles will run to infinity. And that's what we want. Since we want the exact area, then we need to allow the norm to run to 0, and so that will allow n to run to infinity. And so as n runs to infinity, then we get this term, which is 4 times the square root of 10 over 3. N runs to infinity, this term will go to 0, 0, 0, and 0. And therefore the exact area is 4 times the square root of 10 divided by 3. And that also leads to the definition of what we call a definite integral. And so this is a limit quantity, and when this limit, when it does exist, is denoted as, this is called a definite integral from a to b of f of x times differential of x, or dx. In this particular example, f of x is the square root of 5x. And then this is a, this is b, so it would be 0 to 2. And this right here represents the limit of this, represents this limit quantity. And this is called the definite integral. And the 0 or the a is called the lower limit of integration. And then the b or the 2 is called the upper limit of integration. And so this is how a Riemann sum works.